So, salmon does have iron in it, but it's not a lot. There's better sources of iron.
The trick is to whisk them really well with a little milk or cream and then cook them low and slow.
Imagine this. You spend 3 months writing Verilog. Your simulation passes, you're proud, and then the synthesis report says, timing failed, power too high, area exploded.
That is not a report. That is a horror movie.
Exactly. If you want to stop this horror movie and actually understand what synthesis is doing to your RTL, stay with us. By the end of this video, you will not just know synthesis, you'll start predicting what the tool will do before it does it.
And if you stay till the end, you can confidently destroy at least 3 interview questions on VLSI synthesis.
Welcome to VLSI Learn with Fun. Let's turn this scary synthesis topic into something you actually enjoy. Welcome, everyone, to VLSI Synthesis, converting RTL to logic gates. And yes, this is not a boring reading of bullet points. This is a conversation between your future and your doubts.
I volunteer to be the doubts. I have plenty.
Perfect. If Jenny understands, anyone watching this on YouTube can understand even at 2 times speed.
Challenge accepted. Let us start before they scroll away.
Let's start with the core question. What exactly is synthesis? In simple terms, synthesis is the process of converting your RTL design, written in Verilog or VHDL, into a gate-level netlist made of real logic gates and flip-flops.
So I write if, else, and case statements, and the tool secretly builds a city of and, or, not, and flip-flops behind the scenes.
Exactly. Your high-level description gets translated into actual hardware components. While doing that, the synthesis tool tries to meet all your timing constraints, keep power under control, and optimize area.
So synthesis is like a translator plus optimizer. It reads my code, speaks gate language, and tries to make it fast, small, and low power.
That's a perfect way to say it. Synthesis is the bridge between your logical design and the final physical implementation of the chip. There are 2 major types of synthesis we usually talk about: logical synthesis and physical synthesis.
Okay, what exactly is logical synthesis?
In logical synthesis, the tool reads your RTL, analyzes it, optimizes the logic, and maps it into generic design elements and then standard cell gates, mostly using abstract timing information.
So it understands my code at a logical level and decides how to implement the functions, but it doesn't fully know where things will sit on the chip.
Exactly. It cares about correctness and timing based on models, but it doesn't yet see the real physical distances between cells.
And physical synthesis is when the tool becomes more realistic and starts thinking about actual placement and floor plan.
Correct. In physical synthesis, the tool uses information from the floor plan and early placement so it can estimate wire lengths and delays more accurately, and then re-optimize logic with that physical awareness.
So logical synthesis is like planning a trip with only distances on paper, and physical synthesis is planning with a real map, traffic, and road conditions.
That's a great analogy. With physical awareness, the tool can do a much better job of timing closure than with purely abstract estimates. Now let's talk about what synthesis needs from you and what you get back.
This sounds like a deal. I give something, it gives something. Hopefully not just errors.
If you give good inputs, it gives good outputs. Inputs are: first, RTL design files, your Verilog or VHDL code. Second, library files, the standard cell libraries and memory macros. Third, design constraints, mainly timing, power, and area specified in formats like SDC. Fourth, technology or tech library files with node-specific information.
So I give it my code, my available building blocks, the rules it should follow, and the details of the process technology.
Exactly. In return, the tool gives you a gate-level netlist in structural Verilog or VHDL, an SDF file that contains delay information, and a set of reports for timing, power, and area.
So the output is basically my design converted into real gates, plus a detailed result card explaining how good or bad it is.
Yes, and just like a result card, you can't ignore those reports if you want a real chip. To make this more concrete, let's take a simple example. Consider a 2-to-1 multiplexer in Verilog. You may write one line, assign y equals select, B:(A).
That line looks so innocent. One line of RTL, no stress.
In RTL, it's one line. But in hardware, synthesis will implement that as a small circuit with an inverter, some AND gates, and an OR gate.
So the tool reads that single line and says, let me build you a proper multiplexer out of standard cells.
Exactly. In the gate-level netlist, you'll see instances like AND2, OR2, and INV with specific cell names from the library, all wired together to implement that mux.
So every tiny line in RTL can expand into multiple gates and paths in hardware. That's dangerous power.
Yes, that's why we always remember that RTL is not free. Everything you write becomes real silicon area and power. Now let's zoom out and look at the overall synthesis process. The main stages are RTL elaboration, RTL to generic logic mapping, technology mapping, gate-level netlist generation, and equivalence checking.
So the sequence is understand the code, build generic logic, map to real cells, generate the final netlist, and then double-check that nothing broke.
Exactly. If any of these stages goes wrong, you can end up with wrong functionality, bad timing, or very poor power and area numbers.
Which covers basically all types of disaster. Great.
That's why understanding each stage gives you much better control over the final design. Let's start with RTL elaboration. In elaboration, the tool reads your RTL, resolves parameters, expands generate statements, and builds the full design hierarchy.
So all those parameterized modules, generate loops, and conditional instantiations become fixed hardware structures at this point.
Exactly. This is also where many basic errors are caught, like missing module definitions, mismatched port widths, and non-synthesizable constructs sneaking into the design.
So RTL elaboration is like the first serious reality check for my code. If my design is messy, this stage will shout at me with warnings and errors.
Correct. If your RTL is clean and consistent, elaboration is smooth and boring, which is exactly what we want. After elaboration, we move to mapping RTL to generic logic. In this stage, the tool converts behavioral constructs like if, case, adders, subtractors, and shifts into a network of generic gates and registers.
These are still not real library cells, right? Just technology-independent logic.
Yes, still generic. At the same time, the tool starts logical optimizations. It removes redundant logic, shares common sub-expressions, and simplifies arithmetic where possible.
So if I write neat and predictable RTL, the tool can see patterns and optimize them well. If my code is weird and inconsistent, it will generate weird and inconsistent hardware.
That is absolutely true. Good coding style clearly helps the synthesis tool create better hardware. Once we have generic logic, we move to technology mapping. Here, the generic gates and registers are mapped onto actual standard cells from your target library.
So instead of a generic AND gate, we now pick a specific cell, like AND2 with a particular drive strength, maybe AND2 with drive 1 or drive 2, depending on the load.
Exactly. The tool decides which specific variant to use based on timing constraints, fan-out, load, and power and area trade-offs.
So at every step, it's basically asking, should I use a faster but larger cell or a smaller but slower cell on this path?
Yes, that choice is at the heart of how synthesis balances timing, power, and area. After technology mapping, we generate the final gate-level netlist. This netlist describes the design entirely as a network of standard cells and wires. There are no if statements or case statements anymore, only cell instances and connections.
So I can open that netlist and see every gate the tool has chosen, with actual cell names and pin connections.
Exactly. Along with the netlist, the tool also produces timing reports, power reports, area reports, and often SDF files with detailed delay information.
And this netlist is what we send into the place and route tools for physical design.
Correct. That's the handoff between logical and physical design flows. Before trusting that netlist, we do one very important step, logic equivalence checking, or LEC. LEC verifies that the RTL and the gate-level netlist are functionally identical for all possible inputs.
Because during optimization, the tool might have heavily restructured the logic, and we must be sure it did not accidentally change behavior.
Precisely. Tools like formality or conformal perform a formal proof that both versions are equivalent.
So if LEC fails, we know something went wrong. Maybe constraints were wrong or some bug got introduced. We fix that before going to physical design.
Exactly. Skipping LEC is extremely risky in any serious chip project. Now, where does synthesis show up in the real industry world? Synthesis is used in ASIC design, FPGA implementation, SoC design, and even in standard cell library development.
In ASIC design, every custom chip, like a processor or a controller,
ASIC design, every custom chip, like a processor or a controller, goes through synthesis to convert RTL into gates.
Correct.
In FPGA flows, synthesis converts your HDL into logic that can be mapped onto lookup tables, flip-flops, block ramps, and DSP blocks inside the FPGA fabric.
And in SoC design, we have many blocks, each synthesized separately and then all brought together on one chip.
Exactly. Library teams also use synthesis-style flows for building and validating optimized standard cell libraries for different process nodes.
So understanding synthesis gives me a foundation to work in multiple domains, ASIC, FPGA, and SoC, not just one.
Yes, it is a very transferable skill. Let us place synthesis in the full design flow. The typical order is specification, RTL coding, simulation and functional verification, then synthesis, then place and route, then final verification and fabrication.
So synthesis sits after I'm reasonably confident about functionality at RTL level.
Exactly. You should not push half-tested RTL into synthesis. First, fix logical bugs at RTL and simulation, then move into synthesis.
And after synthesis, we keep iterating, adjust RTL or constraints, rerun synthesis, check timing and power, and repeat until we reach closure.
Exactly. Especially near tape-out, this modify and resynthesize loop is very intense. Now, why is synthesis such a big deal? Synthesis directly affects timing, power, area, manufacturability, and reliability.
So if synthesis is poor, my chip can end up slow, hot, big, and unreliable. That's pretty much everything you do not want.
Exactly. Done well, synthesis helps you close timing at your target frequency, reduce both dynamic and leakage power, and minimize area to reduce cost. It also ensures that the design is implementable in the target technology, respecting the available cells and rules.
So synthesis is not just some compiler step, it's a central optimization step that decides how good or bad your design becomes in real silicon.
That's exactly the mindset you should have. Let us talk about tools now. In industry, some common tools are Synopsys Design Compiler for synthesis, Formality for equivalence checking, and Power Compiler for power optimization. Cadence Genus for synthesis and Conformal for logic equivalence. Mentor or Siemens Precision RTL for synthesis and Catapult for high-level synthesis from languages like C or C++.
For FPGAs, we usually hear about Xilinx Vivado and Intel Quartus, right? They have their own built-in synthesis engines.
Correct. In the open source world, YOSYS is a very popular synthesis framework, and platforms like EDA Playground let you try small experiments online.
So these names are like the tool vocabulary of a VLSI engineer. If I know them and roughly what they do, I sound much more professional in interviews.
Absolutely. Combine tool names with strong concepts and you are in a great position. One very important topic is constraints, especially SDC. The Synopsys Design Constraints file tells the tool exactly what timing requirements and special paths it should consider. In SDC, you define clocks, their periods and waveforms, input and output delays, generated clocks, virtual clocks, false paths, and multi-cycle paths.
So SDC is like the tool's rulebook and contract. If I write it badly, the tool will optimize the wrong things or ignore real problems.
Exactly. Forgetting to declare a false path can make the tool waste effort fixing something that doesn't matter. Misusing multi-cycle paths can hide real timing violations and create silicon bugs.
So constraint writing is not a side job, it's a key skill.
Yes, good constraints plus good RTL equal good synthesis. Synthesis is usually iterative. Let us talk about that loop. The typical cycle is: Step 1. Run synthesis with your current RTL and constraints. Step 2. Analyze timing, power, and area reports. Step 3. Adjust RTL or constraints and then rerun synthesis. Repeat this process until timing closure and all other goals are met.
Sometimes the fixes in RTL, like breaking a long combinational path into 2 pipeline stages, sometimes the fixes in constraints, like setting realistic clock periods.
Exactly. Near the end of the project, this loop becomes very focused, trying to eliminate the last few timing violations and power hotspots.
It sounds painful but also satisfying when reports finally turn green.
Yes, that all-green moment feels amazing. Now, let us mention some challenges in VLSI synthesis. First, balancing multiple constraints like timing, power, and area is hard. Second, large designs with millions or billions of gates require very efficient algorithms and a lot of memory and time. Third, timing closure is often difficult, especially at advanced process nodes. Fourth, power dissipation, both dynamic and leakage, must be controlled. Fifth, design must remain testable, so DFT requirements must be satisfied. And sometimes, certain combinations of constraints are simply not achievable.
So in real projects, you sometimes change the design, sometimes change the constraints, and sometimes even the product requirements to find a realistic balance.
Exactly. Chip design is always about intelligent trade-offs. Let us wrap up everything we have discussed. VLSI synthesis is the critical bridge between your RTL and the real gate-level hardware that goes into silicon. It reads your RTL, uses libraries and constraints, optimizes the design, and produces a netlist that aims to meet timing, power, and area goals.
It fits into the flow after RTL simulation and before physical design, and it's used heavily in ASIC, FPGA, and SoC projects.
We saw what synthesis is, how the flow works, what inputs and outputs it uses, where it sits in the design flow, why it is important, and which tools are commonly used.
If you master RTL coding, understand constraints, and learn to read timing and power reports, you'll be far ahead in your VLSI career.
And this is exactly what VLSI Learn with Fun is for, turning scary topics like synthesis into something you can actually enjoy and remember.
If you watch till here, I know you're serious about this field.
Don't forget to subscribe to the channel. Right now, we are at almost 0 subscribers, and you can proudly say, I was here at the beginning.
Comment below which topic you want next: constraints deep dive, STA basics, or the complete flow from synthesis to timing closure.
Share this video with one friend who is scared of synthesis. Let us reduce fear and increase understanding.
Thank you for watching. Keep learning, keep experimenting.